Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back everyone to ITDR2103. Today's session is continuing the one uploaded earlier, which is a graph theory. It's really important you check the graph theory one because it got a lot of definition and terminologies, and then you come back to the session. In this session, we will discuss about the matrix representation of a graph, agency matrix, and isomorphism. Now, we used to represent a graph using the triple, where we introduce the set of vertices, set of edges, and the incidence function. And the incidence function, either we write it as g of v, represent the connection between v and v for each edge in the graph, or we can use the incidence table. And basically, the incidence table depend on the type of graph because it differ in the undirected graph or the directed graph. Okay, because in the directed graph we do have in degree out degree, while undirected graph is the edge and which vertices are connecting. Now we got something else to represent a graph, which is a matrix or the agency matrix. Agency matrix is basically a square matrix, and we are labeling it as AG. A square matrix means the number of rows are equal to the number of columns in this matrix, and they are usually n by n, where n is the number of vertices in this graph. Now each entry, Aij, is representing a number of edge from Vi to Vj. So here we got the vertex 1, vertex 2, vertex 3, and here we got again vertex 1, vertex 2, and vertex 3. Now the entry here represents the number of edges that comes from Vi to Vj. All right, this is the agency matrices. Let's see this example here. We got the following graph and we need to write the agency matrix of the graph. So first thing we do is we just have to put the square brackets. Now the size of this graph is n by n, which is the number of vertices in the graph. And if you can see here, it's supposed to be 4 by 4. So I have 4 rows and 4 columns. Each row represents the vertex we got. So here V1, V2, V3, V4, and here we got again V1, V2, V3, and V4. Now, as we mentioned before, each entry shows the number of edges between vertex and the other vertex. So if we start here, between V1 and V1, do we have any edge? No, we don't have. So here we got 0. V1 to V2, if you can see here, there is 1 and 2. So from V1 to V2, we have 2 edges. V1 to V3, we got 1 edge, and V1 to V4, 0. So we'll do this again for the rest of vertices in this graph. V2 to V1 is 2, V2 to V2, 0, V2 to V3, we got 1 edge, and V2 to V4, we got also 1 edge. All right, now let's see V3, V1, there is 1, V3, V2, 1, V3, 0, V3, and V4 is also 0. Now V4, V1 there is no edge. V4, V2, there is one edge. V4, V3, there is no edge. And V4 and V4, there is one edge. And here we write the adjacency matrix of a graph. How if we got the opposite? We do have the agents here, the matrix here, and we need to draw the graph itself. So if you can see here, we got this matrix of size 1, 2, 3, 4, 5, 5 by 5. So that means we have 5 vertices in this graph. So here we got V1, V2, V3, V4, and V5. Now we'll go one by one. Here, V1, and here we start with V1. The edges between V1 and V1 is 1, so that means we do have a loop here. V1 and V2, 0. V1 and V3, 1. V1 and V4, 1. And V1 and V5 are 0. Here we got V2, V1, 0. V2, V2, 0. V2, V3, 2. So here 1 and 2. Then V2, V4, 0. V2, V5, 1. All right. V3, V1 is 1, which is what we have here. V3, V2 is 2. We've already drawing. V3, V3 is 0 and 0 and 0. V4, V1 is already there. V4, V2, no connection. V4, V3, no connection. V4 and V4, there is 1. V4 and V5, there is also 1. Then we have V5, V1 is 0. V5, V2 is 1. V5, V3, 0. V5, V4, 1. V5 and V5, 0. And here we got the graph. Now, if you notice here, if I have a link between V1 and V3, then I supposed to have a link between V3 and V1. Okay, now if we can see here, V1, there is a link to V3, and if you notice here, V3 and V1, there is a link. And in matrix, we call this as symmetric, where if we got a link between A and B, then we're supposed to have a link between B and A. And basically, the symmetric should be in the agency matrix for the undirected graphs. All right, so here's the note. If G is an undirected graph, then AG will be symmetric matrix. However, if it's a directed graph, then it might be or might be not a symmetric matrix. Let's see this example in order to understand if they are symmetric or not. So here the agency matrix of the following D graph. We have a D graph here. We want to write the agency matrix. So let's have it a name, which is AG. And it will be of size 4 by 4. Now, we can see here that there is a link between V1 and V1. no link between V1 and V2, no link to V3, no link to V4. V2 has a link to V4. So here V2, there is one link to V4 and there's one link to V3. V4, if you can see here, there is no edge coming out of V4. So here we got 0, 0, 0. Sorry, this is the V3 and also V4. So this is what we mean by in the agency matrix, if there is a link between V2 and V4, it's not supposed to be there is a link vice versa. So the links in directed graph usually counted as from the one is coming out the arrow to the one is going to. All right. Now the agency matrix of directed graph or D graph need not to be a symmetric matrix, but set time it will be asymmetric. Let's see if we got the agency matrix and we want to draw the directed graph. Now here from this agency matrix we can see that we got 3 vertices. Okay, there is a link from V1 to V2 and it's really important we show the arrow. There is a link from V1 to V3 and also there is a link from V1 to V1. V2 has a link to V1, no link to V0, there is a link to V3. V3 has a link to V1 and V3 has a link to V2 and no link to itself. So here we draw the directed graph. Now if we got the same matrix but for undirected graph, it will be different than this. All right. Sometimes in drawing the graphs using agency matrix, we prefer to name each entry here as an edge. So here we got edge 1, here we got edge 2 and edge 3. Then edge 4, edge 5, and here we got edge 6 and edge 7. It is a really good practice when we label everything in a graph. The second part of our session today is talking about isomorphism. And isomorphism, when we got two graphs, all right, G1 is said to be isomorphic to G2 if there is existing of one-to-one corresponding vertex 1 to vertex 2 and one-to-one correspondence E1 to E2, such that for any edge AK in E1 vertex VIVJ are end vertices of AK in G1 if and only if I, if J are vertices of HEJ. What do we mean by this? We mean that if we got two graphs, then basically they should be the same. How we can measure if they are isomorphic or not? By looking out of these rules. First thing, there is existing of one-to-one corresponding between the set of vertices of edge in two graphs. All right, now first thing is we need to make sure that the number of vertices in the two graphs are equal. Then we need to check that the number of edges in those two graphs also are equal. Then we need to check the degree sequence in the two graphs. They should be also equal. Then we need to have the one-to-one corresponding vertices and one-to-one corresponding edges. And here we will see what do we mean by that. All right, now let's move this example. We got two graphs, graph 1 and graph 2, and we need to check whether they are isomorphic or not. In order to do so, as we mentioned earlier in the isomorphic definition, we need to make sure that we got the same number of vertices in graph 1 and graph 2, the same number of edges in graph 1 and graph 2, the same degree sequence, and then we can check the one-to-one corresponding between vertex sets and one-to-one corresponding between edge set. So let's start with first condition, which is number of vertices. In graph 1, we can see that they are 6 vertices. In graph 2, we can see that also they are 6 vertices. Moving to the number of edge. Number of edge here is 1, 2, 3, 4, 5, 6 on graph 1. And here we can see that they are 1, 2, 3, 4, 5, and 6. Degree sequence. V1 has 2 edges. V2 also 2. V3 2. V4, V5, and V6. Each vertex in graph 1 has 2 edges. In graph 2, also the same. E1 got 2 edges. E2 also 2. E3 2. E4 2. E5 2. And E6, U6 also 2. So they are U. So here we got 1, 2, 3, 4, 5, and 6. Now we need to check that each vertex in graph 1 has the same in graph 2. Alright, so we can see here that V1 of degree 2 is having the same here as U2. So V1 is represented by U1 in graph 2. V2, the one which is linking to V1. So I need to find the links. Here U1 is connected to U2 and U3. So if we can see that here, U2 is the one represented by V2. So V2, U2, V3, that connecting to U2, V2. So U2 is connecting to V3, which is connected to U2 and U4. V4, U4, V5, U5, and finally move here. V6 is represented by U6. Sometimes the order won't be the same, or the numbers are not the same. So we need to check that the linked vertices in graph 1 are also linked in graph 2. Now moving to the third condition, which is E1 and E2. So one-to-one correspondence between edge set. E1 that connecting V1 and V2 are represented here by F1. So E1 is F1 in graph 2. E2 is represented by F2. E3, we can see that it is F3. E4, F4, E5, F5, and E6 is F6. Again, sometimes the labeling won't be the same. The order is not the same. So what we need to check is the link between V1 and V2 supposed to be in graph 1 with corresponding vertices. So the one represented V1 in graph 1 is U1. The one represented V2 in graph 1 is U2. Then this edge represented here as this edge. So we got the same number of vertices, same number of edges, same degree sequence, and we got the one-to-one correspondence between vertex 6 and one-to-one correspondence between edge set. So graph 1 and graph 2 are isomorphic. isomorphic. So they are same with different shape. Another example here, and we got graph A and graph B. And if you notice, there's no, we can see that the edges are not labeled. So we will do the same. We will check each condition. So number of vertices, if we can see here, we got 1, 2, 3, 4, 5, and 6. In graph 1, there is 6 vertices. In graph 2, we got 1, 2, 3, 4, 5, and 6. So the first condition met successfully. Number of edges, we can see that they are here. 1, 2, 3, 4, 5, 6, 7 edges. And here we got 1, 2, 3, 4, 5, 6, and again 7 edges. The degree sequence. So in V1, we can see that it's connecting 3 edges, V2, 2, V3, 2, V4, 2, V5, also 2, and V6, 3. Alright, how about graph 2? U1 is connecting 1, 2, 3, 4, and 5. U2 is connecting 1. U3 is connecting 2 edges. U4, 2. U5, also 2. U6, 2. And if you noticed here that the degree sequence are different from graph 1 and graph 2, because here we got a vertex with degree 5, while here we don't have a vertex of degree 5. What is more, here we got a vertex with degree 1, which is not there. And in graph 1, we got 2 vertices with degree 3, while in graph 2, it doesn't have any vertex with degree 3. Therefore, we consider that graph A and graph B are not isomorphic. All right. And here we reach the end of this session, where we discussed about matrix representation of a graph, which is agency matrix, and isomorphism. Thank you for listening. We'll see you inshallah in the next session.